Okay, now we start with a continuation of Lev Beklemishev's tutorial.
Thank you very much. So, yesterday I finished with formulating this very general result, approximately formulating the very general version of Gödel's second incompleteness theorem due to Pudlak. And in contrast with this result, I promised to give a counterexample due to Dan Willard of a reasonably axiomatized, reasonably defined, but weak arithmetical theory for which the Gödel's second incompleteness theorem does not hold. And I would like to begin with this counterexample because it's somehow simpler than explaining all the details in Pudlak.
Was that the guy who proved P diffidently?
What?
This Dan Willard, was he the guy who proved P diffidently?
I don't know whether he proved that. Actually, related to that question, I can say that he published a lot of papers on that topic. In fact, both in terms of numbers of pages and in terms of numbers of papers, maybe about 7 or 10 papers, and among them good publications like in JSL, several papers, and Apple, several papers, and so on. So obviously this topic very important, but it's all variations on the same theme, and somehow what I will be presenting is somehow the most simplistic version of what he does. I had to go into this topic actually in connection with reviewing his work in connection with this Gödel Fellowship Prize, which will be awarded soon. But so before that, well, I don't think that there are many people who have actually read and understood what he wrote, but I think that basically everything is correct, at least in those parts that I studied, and they're sufficiently nice to know about. So that's okay. So the idea that we are going to present a weak theory, essentially a theory of arithmetic, which proves its own consistency. And this theory is constructed on 2 stages. First, we formulate a sort of a base theory T0. Which does not prove its own consistency, but which is a kind of normal, well-defined canonical theory, so to say. And the point is that we change the language. So instead of dealing with the canonical language of piano arithmetic with operations of plus, times, and successor, first of all, what we do, we forbid, instead of dealing with functions, we deal with these relations. So we don't want to have functions which have any growth. So let's define, so let's give a definition. So let's say that a function f of x, also from natural numbers to natural numbers, is non-growth.